All right, so back in the saddle again. Like I mentioned before, I'm coming out of narrative retirement, putting together some new PowerPoints reflecting of some new material we recently added to the course. No array of stuffed animals this time. It's just you and I. So rehashing our previous PowerPoint, our whole goal is to apply some of these cool inferential techniques, what I called the molecular building blocks of statistics, confidence intervals and hypothesis testing, apply them in the context of regression. We said there's three situations we might do that. That first bullet point we already talked about. What we're going to talk about in this slide are those next two bullet points, which is essentially two different types of confidence intervals that are very, very useful for researchers in terms of applying regression techniques. I'm still going to work in the context of this bear problem. So just to remind us, it was mere seconds ago that I narrated that last one, but I need to keep in mind, as far as I know, it was weeks ago since you last listened to it. Our regression equation, just to review, just from the last one, was that the weight of a bear, our best guess, our sort of y hat, was negative 441.4 plus 10.338 times x. Our x variable in this case is length. Here was some Minitab output that showed us a significance test for the slope. We had a test statistic, which was 21.42. We had a p-value, which was immeasurably small. Looking at that output, all we know is it's less than 0.001, right? Because if it was 0.001 or larger, there's room there for it. But it just put a bunch of zeros up to that particular decimal place. That, of course, is much less than our usual 0.05, so we say that our slope is significantly different than 0. There did appear to be a relationship between x and y. This is a useful equation. Pretty cool. Now, where do we go from there? Well, once we have a useful equation, well, why don't we use it? And how can we use it? What's the utility in regression? We talked about the utility when we talked about regression so many moons ago. We said that the slope itself is often useful. That is, the slope quantifies a particular relationship. We might know that there is a positive or negative relationship between x and y, thanks to perhaps the correlation. A positive correlation would say that as x increases, y tends to increase also. The slope goes a little deeper. It says, by how much do we expect it to increase? Or decrease in the case of a negative slope. We also talked about prediction. We said that these regression equations are really, really good, really useful for making predictions. If you're Pico, you could use the temperature of a given week to predict what the fuel consumption in Philadelphia is going to be, and hence how much you should order, how much you should have on hand. If you're a tire manufacturer, and you can look at the relationship between between mileage and tread depth, you could use that and generate a prediction for what is the mileage associated with a particular tread depth that has become like a dangerous threshold. You could predict what mileage that danger threshold will be reached, and you could encourage people to replace their tires once they reach that threshold. So these are two primary uses. We talked more about slope and how to do a significance test of slope. What we're going to do now is we're going to talk a little bit more deeply about prediction. Now, recall from before that it's real simple to make a prediction for a given linear equation. If we want to predict some value of y for a given value of x, all we do is we plug that value of x into the equation. Example, if we wanted to predict the weight of a bear that has a length of 60, guess we're getting ready to tranquilize it, so some kind of rowdy bear that's giving us a hard time. Then all we would do is we'd take that linear equation and we'd plug in 60. Verify that that's 178.88. So if all I know is that a bear's length is 60, my best guess for how much that bear is going to weigh is 178.88 pounds. However, this point estimate does not take the inherent variation that is found in life, in nature, in the universe into account. Even though our best guess for how much a 60-inch bear would weigh is 178.88 pounds, we would nonetheless be surprised if it weighs exactly, oh dear, there's a typo there, if it weighs exactly 178.88 pounds. Right on, precisely, not 178.881, but exactly 178.880. That is, the probability of that happening is essentially zero. Just like it's essentially impossible for the sample mean to dead on bullseye equal the true mean, just like it's impossible for our parents right down to the nanosecond predict exactly how long it takes to drive from your house to grandma's house. Just like all these things are impossible to predict with the type of precision implied by our point estimate. Nonetheless, we do expect our point estimate to be very close. That is, we'd be surprised if the bear weighed exactly 178.88, but we do expect it to weigh close to 178.88. And so the question becomes, and this is always the question that motivates confidence intervals, is, well, how do we quantify that closeness? And here they are, coming back to haunt us. That's actually a bit of a pejorative phrase, right? Because it's like it's likening it to some sort of ghost or monster. I should say coming back to delight us. Here are confidence intervals coming back to delight us. And these confidence intervals are going to help us figure out sort of what is a plausible range of values for the weight we might expect if we know that we have a bear with a length of 60. This particular situation is referred to as a prediction interval. There's actually a second type of confidence interval that's also useful to researchers. It's subtly but importantly different. It's 2 for 1 day in Math 121. It's a confidence interval for the mean of y. So in this example, it's a confidence interval for the mean weight of all bears with a particular length. We call this a confidence interval for the mean. So we'll elaborate in a few slides, but we have essentially two different intervals, right? Two different questions we might answer. We might say, if I had one particular bear, my BBF, my best bear friend, instead of BFF, BBFF, my best bear friend forever. And I know that his length is 60. If I wanted to try to guess, right, a plausible range of values for the weight of that actual bear, of my BBFF, right, that's the prediction interval. However, if I wanted to sort of look at it's kind of like a slice, right, like a subgroup or a subdemographic, instead of all bears, what if I only focused on bears with a length of 60? There's still lots of such bears, right? Thousands and thousands and thousands of bears whose length is 60 inches. Some of them are hefty, some of them are scrawny, but we could ask the question, of all the 60-inch bears, what's their mean weight? What's the average weight for all bears with 60 inches? This is called a confidence interval for the mean. Now, both of these intervals are centered at our best guess. So if we're talking about 60, then our best guess is at 178, 179 pounds. However, so they're both centered at the same value, but the confidence interval for the mean is smaller than the prediction interval. Huh. Does that make sense? It does, right? Because it's maybe a little intuitive to us by now that there's less variability associated with with a sample, with an aggregate, than there is with a single value. Right? It's harder to predict just sort of one person in contrast to like the whole overall mean of that particular population. It's analogous to what? It's analogous to what we observed with the central limit theorem. Remember, the variation or the standard deviation for a single observation was that sigma, but remember, what was the standard deviation for the sample mean? It was sigma over the square root of n. That sample mean had smaller standard deviation than a single observation, and hence had a smaller confidence interval. This is kind of the same idea. Now we could ask a software program to generate these confidence intervals for us. The formulas are pretty crazy. Certainly would never do them by hand, and plugging the information into a calculator, right? Calculator could do the calculations pretty easy, but actually hand typing all the numbers, all the weights and lengths of the bears into the calculator would be tedious. It's much easier just to find the data set which is already existing as an Excel file and import it into Minitab. That's what I did. I asked it to generate the intervals, and there they are. So the equation we can see is up top. It says length 60, so we're generating these values for an x, for a length of 60. Where it says fit, that's our best guess. We had 178 point, what was it, 0.88. So they got a slightly different number, 178.902. I'm assuming I did just a little bit of rounding that the software package didn't end up doing. And there are two confidence intervals. The rightmost confidence interval, the one going from 72 to 285, that's our prediction interval. We'll interpret that on the next slide. And then the slide to the left of it, or the confidence interval, sorry, to the left of it, that one that goes from 169 to 187, that's the confidence interval for the mean. As anticipated, the confidence interval for the mean is the smaller of the two, or right, flip side, the prediction interval is the larger of the two. So let's look at the interpretation of these. In terms of the prediction interval, we would say that we are 95% confident that the actual weight of a single bear with a length of 60 is going to be somewhere between 72.2091 and 250 or 285.595 inches, right? So I would expect the weight of my BBFF to range somewhere between 72 and 285. It's a pretty large range of values, which is indicating a lot of variability in our data, as well as, I guess, a relatively small sample size. Now, our confidence interval for the mean says this, and notice this is a much smaller, much more precise interval. It says that we are 95% confident that the mean weight of all bears with a length of 60 is somewhere between 169.928 and 187.876. Pretty cool, right? Well, that wraps up regression, at least in terms of the depth that we're going to go into it. So, in the immortal words of our dearly past Eric the actor, bye for now.